Today, I want to look at one of the problems that had one of the parts was technically something that we didn't cover, but technically also kind of something that we did cover. And because one of the questions involved this. And then you had various information about F and G and stuff like that. So the reason I wanted to go about this, look at this problem, I put 1, 2x because I couldn't remember if it was 3, 4, or 5 the day that this one showed up. I'm pretty sure it was part D or whatever problem it was. So I can put that. The reason that I wanted this problem is that this, if you've had like a full dose of calculus, this is an integration by substitution problem. So when you look at this, those of you who have seen into the future, I know some of you are looking into the future. You might be looking at this and thinking integration by substitution. But now I've just written integration by substitution. You'll be thinking, dude, that doesn't show up until chapter 7, section 1. How could you do this to us, you bastard? Well, it doesn't matter that I haven't talked about integration by substitution because we have talked about where this comes from. So integration by substitution, though we haven't done that yet. That looks more shocked. Put some teeth in there. Grr. We haven't done chapter 7, so what's this integration by substitution? It's okay, because integration by substitution is just anti-chain rule. Not like opposed to chain rule, it's chain rule in the other direction. It's not like we're protesting the chain rule. It's that we're just doing the reverse of the chain rule. So integration by substitution is an anti-chain rule. It's the integration version of the chain rule. Remember, the chain rule says that the derivative of a composition of functions is the derivative of the outside with respect to the inside times the derivative of the inside. The big deal is in the chain rule is that we multiply by the derivative of the inside. Take the derivative of f with respect to g and multiply by the derivative of g with respect to x. In Leibniz notation, we'd say df dx is df dg, the derivative of f with respect to g, times the derivative of g with respect to x. And we say, oh, look, it's like fractions. It's like the dg cancels. And students are like, oh, is it like the dg cancels? I'm like, oh, by the time the difference matters, you'll be out of this class. So yeah, totally like that. So if the chain rule says the derivative of f of g of x is f prime of g of x times g prime of x, we know the relationship between differentiation and integration means we can turn this around and turn it into an integration. So this, if we turn it around, if we integrate f prime of g of x times g prime of x dx, that will give us f of g of x plus some constant of integration. Chain rule one way, integration by substitution the other way. Chain rule going this way, integration by substitution. So even though we haven't talked about integration by substitution, we have talked about chain rule. And this is just an application of the reverse chain rule, the anti-chain rule. And that's what you were expected to recognize. That's what some of you were expected to recognize. That's all what happens on a test. Oh, it wasn't a test. I shouldn't use that word. On a problem. Forget that I said test. I'm not allowed to Jedi mind trick your memories. Forget that I said test. But the expectation was some of you would recognize this and say, this looks like the result of the chain rule. Then you go onto the Google and say, what does the chain rule say? No, not that one. No, not that one either. Yes, that one. This is what that looks like. So the antiderivative of f prime of g of x times g prime of x is just f of g of x. And this is information that we have. So the chain rule says, or the anti-chain rule says that this will just be f of g of x. And it's a definite integral, so we'll evaluate from -2 to 3. So this will be f of g of 3 minus f of g of 2. And in the problem, we had g of 3 and g of 2. And so then, therefore, we had f, and we had also f of whatever g of 3 was, and f of whatever g of 2 was. So that was your strategy for this particular problem. So when the problem shows up on Canvas, you'll know what to write. You'll recognize not integration by substitution, but you'll recognize the chain rule and use it backwards. Because that's the idea behind the problems that we've been doing the last couple of weeks. Can you recognize the things that we do know, that we definitely know, in a context that we don't normally see them? Oh, f of g of -2. As I said it, I was sitting there thinking, wait, we don't know -2. What the heck? So from the table, if we look at g of 3, g of 3 is equal to 1. That's from the table. And g of -2 is equal to -1. And so we want f of 1 minus f of -1. And those are the other two values that we have. F of 1 is 2, and f of -1 is 8. This was really poorly planned. I don't know why I went up instead of down. So f of 1 is 2, and f of -1 is 8. And these also came from the table. Any questions? This part. Oh man, you didn't see it. I could have fixed it. Oh well, that's fine. Any questions? I kind of did this in a jacked up order. It kind of like went from here, and it kind of goes up to here where we used the table the first time, then it goes down to there. where we use the table for the other values. So yes. F of 1. Yep. Yeah. And it's just bouncing you around to different parts of the table. Yes. Yeah. Yeah, we're just playing with the composition, and the table cleverly gives you the values that you need. Like if the table was set up so that G of 3 was equal to 5, we don't have that. So that would be an example of a poorly written problem. And I promise you, I've never done that before. Like expected people to find values that aren't on the table. But that's why you steal problems, because they've been vetted. How's everybody okay? Happens sometimes. You write a problem and you think it's going to work a certain way, and because you think it's going to work a certain way, you just let it go. You just run with it, and then you actually sit down while students are working on the problem. You actually sit down and do the problem. You're like, oh shit, this is not going to work the way I thought it was going to work. And the only option is to catch it before someone comes up to you and says, hey, this problem isn't working. You'd be like, oh, what? That's crazy. Any questions? Bottom line, always vet your problems before you send them out. Do the problems, don't expect them to be a certain way. Students have a version of this as well. I don't know if anybody, if you're taking a test, if you check your answers, but the time to check your answers is not immediately after you've done the problem. Because let's say the mistake on the problem that you're doing is you said 3 times 5, 8. If you immediately check your answers and go over the work that you just did, in your mind, you're still thinking that 3 times 5 is 8. You're still wrong about that. But if you put some time between the time that you said 3 times 5 is 8, and you do some more problems and then come back to it later, then you'll be able to notice. If you look right away, you still have that wrong information loaded into the short-term memory. But if you give it some time, the cache gets cleared out, and you're like, oh, what? 3 times 5 is 15, not 8, right? And then your short-term memory is like, oh, I don't know. I just ran with it. So always come back to the problem later. Give the cache some time to clear out. And then go back to the problems and check your answer. You know what I mean? Most students don't do that. They just like, all done, and then they walk out. And that's the equivalent of me giving out a faulty problem. So we all do it. How's everybody okay? My favorite move is like turning the test in, walking out, and then realizing I made a mistake. Like I get all the way out the building. I'm like, oh, hang on a second. Did I just do that? And then you go running back in, and the professor's like already marked you wrong. And I go, Dr. Glass, 3 times 5 is not 8. And I go, minus 10. I said it that way because the whole thing happened in slow motion. Any questions? So the exercises were about recognizing things in different contexts, and that brought us to this cool one, this integration by substitution. We want to be able to recognize when a derivative was found with substitution, so that when we go backwards, we know what we can what to do. So, for example, if I want to find the derivative with respect to x, let's say, of cosine of x squared minus 3x minus 4. We know we're going to find the derivative with the chain rule. I've got cosine of some stuff. The derivative of cosine of some stuff is negative sine of that stuff. I wanted this. It's fine. It's fine. Stop worrying. Times the derivative of that stuff. What we want to look for is we're not about just finding the derivative. It's week 13. We've talked about the chain rule for a long time. It was a long time ago. It should be automatic to us right now. What we're looking for now is to recognize if I don't have the derivative of cosine of x squared minus 3x minus 4, if we look at this, we can see that this is the derivative of x squared minus 3x minus 4. So our goal now is to see more stuff than just what we're looking at. We want to look at this and see oops. I'm going to point out the thing that we're actually looking for. We want to see that 2x minus 3 is the derivative of x squared minus 3x minus 4. That's what we want to see in this derivative, in this function. When we put it in the context of the derivative, it's easy to spot because I asked you to find the derivative. But we want to be able to see it out of context. So if I say something like the integral of sine, I'm going to write it all in a funky order too. Not really a funky order. We want to see this minus 2x minus 3 times sine of x squared minus 3x minus 4. We want to see that 2x minus 3 as the derivative of the x squared minus 3x minus 4. Not just in this context because we just found this derivative with the chain rule, but we also want to see it in this context as well. So that when we look at this integral, we say this integral was found with the chain rule. You want to recognize that that 2x minus 3 is just there to be the derivative of the inside. You want to recognize when you have the derivative of the inside as a factor. Because that's an indication that we're dealing with something that was found with the chain rule. And so you can just undo this. Because in math, we have to know things backwards and forwards. Pause the copy. Oh, I'm not supposed to do that part. The reason we want to look for things like this is we want to recognize slight variations on this. Here we've changed. What's missing is the negative. We know the derivative of cosine is negative sine, and if the negative isn't there, then it must have been canceled out. So instead of just cosine of x squared minus 3x minus 4, it must have been negative, so that we multiplied a negative times a negative, we got a positive. We want to look for variations on this theme. The core of the problem, the core thing that we recognize is that that 2x minus 3 That's the derivative of x squared minus 3x minus 4. And the x squared minus 3x minus 4 is plugged into the sine function, which is the derivative of negative cosine. So this was found with the chain rule. I want to look for variations on a theme. That 2x minus 3 is the derivative of x squared minus 3x minus 4. And x squared minus 3x minus 4 has been plugged into an e to the x function. So what we're really integrating here is the f function. F prime is e to the something. And that means f is e to that thing. And if we want to check to see if this is right, we take the derivative of e to the x squared minus 3x minus 4. The derivative of e to the x squared minus 3x minus 4 is e to the x squared minus 3x minus 4 times the derivative 2x minus 3. Questions? That's everybody okay? Everybody's like, oh, yes, I can see how critical this is going to be when I'm working on the mission to Mars for a cabal of billionaires who are trying to leave Earth and colonize Mars. Because they're paying you a lot, but not that much. Not so much that you'll be able to join the club and actually go with them to Mars, right? So instead of working on the spaceship that will get us from Earth, or us, like I'm in the billionaires club, secretly I am, I've got teacher money. So instead of being on the team that's building the rocket ship from Earth to Mars, be on the environmental systems team that's going to maintain the environment on Mars. That's called planning ahead. Remember one of the things that we did when we were first learning how to integrate functions, when the only tool that we had was the integral of x to the n is x to the n plus 1 over n plus 1, where we add one of the exponents divided by the new exponent. One of the tools that we had was to just multiply everything out. The problem is, in something like this, we don't want to just multiply everything out. I've got x squared, I've got a quadratic raised to a fifth power. It's going to be a lot of terms. I don't want to multiply that out. And then I'm going to have to multiply that again by a 2x minus 3. Sometimes you do this and people like look up the expanded version of these polynomials on Wolfram alpha. I'm like, oh, dude, if you're going to look at Wolfram alpha for the expansion, just look at Wolfram alpha for the antiderivative. But what we see that 2x minus 3 is only there to be the derivative of the inside. So what we're actually integrating is something to the fifth power. And the integral of something to the fifth power is 1/6 that thing to the sixth power. So the derivative of and we can check, the derivative of 1/6 stuff to the sixth power is stuff to the fifth power times the derivative of the stuff. So the idea here is we want to recognize when the chain rule has been used. How's everybody okay? How can we think of calculus? Such a gatekeeping class. You want to take physics. It's like, I'll never do calculus first. It's like, well, you have to do this class first before you get to do physics. At least chemistry is like, oh, sure, come on in. Physics is like, oh, no. Even though the calculus class be like, oh, physics, the way that we talk about calculus in math class is kind of different than the way you talk about calculus in physics class. You like do like all physics talking of calculus, but calculus is doing like all math talk of calculus. And they're kind of different. And physics is still like, oh, no, I want to seem superior by requiring prerequisites. How's everybody okay? All right, so that if you're wondering if this was the entire point of that one problem, yeah, this was the entire point. I knew it had that substitution. I'm like, oh, but we haven't done substitution. That's what made the problem fun for me. Fun for me. I don't know about for you. I knew what day this was on last week. I'm like, oh, and so Wednesday, while I was traveling and we were getting diverted to Salt Lake City, I was like, oh, but at least my calculus students had that cool substitution problem. And then I thought, oh man, maybe I should have told Professor Kwan not to do integration by substitution. I just answered like a math professor, like, oh, I don't know. What do you think? And the students be like, oh, you son of a bitch. You answered a question with a question. Classic teacher Uno reverse. All right, that's going to do it for today. I'll see you all on tomorrow. We'll talk more about some of these problems. Everybody have a good day, and thanks for playing.